Good morning, everyone. Thank you, April and Eric, for giving me the chance to present on a project which just ended a few months ago. And this project was through NCHRP, and it was looking at improving the guidance to ASTM C1778 for preventing alkali-silica reaction in concrete. And I just want to kind of give a shout out here to my all-star team of, on this project. It was 3 different universities, University of Texas, University of New Brunswick, and also actually 4 universities, Benoit Fournier at Laval University, and Jason Eidecker and his team at Oregon State University. So 1778, I think everyone here probably knows of 1778, otherwise I don't know why you would be here at 8:30 in the morning after the mixer. But 1778, as we know, is kind of the standard guide of looking at ASR and ACR, and what do you do if you do have ASR, like different or reactive aggregates in different prevention levels? So this project kind of looked at, this was probably after about 10 years, and we're kind of trying to look to see if it's still really up to date. And the whole goal was to try to improve 1778. And if we look at 1778, it is very similar to ASTO R80, and these guide documents kind of have 2 different steps. One is how do you evaluate your aggregate reactivity, and if your aggregate is reactive, how do you select preventive measures? Do you do a prescriptive approach, or do you do a performance-based approach? So the background on these guidance documents comes from years and years of long-term data, mostly kind of looking at benchmarking laboratory tests to field exposure blocks. These are a couple of the different sites that we have exposure blocks at. The site on top left here is the one in Austin, Texas. Then there's the CanMet site in Ontario, Canada, and a newer site in Corvallis that Jason Eidecker has set up, and also in Fredericton, Canada, and also in Tree Island, Maine. So a lot of test methods have been done, and then we've also cast these blocks to try to benchmark these test methods. So when I say exposure site, what do I mean? So this is our site in Austin, Texas. We now have over 1,200 of these blocks, each with different types of aggregates from all across the country, and all new types of, or not new types, but with lots of different preventive measures to try to see how we could slow down the reaction or stop the reaction from occurring. This is just one of the blocks. It's about 3.5 cubic feet. Weighs good amount, and it's a good workout when you start making a whole bunch of these blocks. But overall, we have these blocks out in the field, and we compare them to test methods. So going back to our 1778, we have, we looked at evaluating aggregate reactivity, and if we try to compare, looking at our existing, so I'm kind of working up on why we're looking at changing the document, not changing, we're fixing, improving 1778. So if you look at our existing exposure site data for just aggregate reactivity, so no SCMs, just straight Portland cement mix, and we're comparing, let's say, 1260 to these exposure blocks, and these, I say here latest age, but that's probably 10, 15 years old. That's how old the blocks are. What you can see is I'll just throw these up here. You want to be in this top right region or this bottom left region where you get good correlation between the test method and the exposure block. And with 1260, what we noticed was, we do get a lot of mixes that look well, good correlation, but we know we do have a lot of mixes which are below 0.1% in C1260. However, they do end up failing in the field, and we do get up to 0.4%. That's a lot of expansion in a block or in concrete. So we kind of have always said that when we look at aggregate reactivity, kind of choose the concrete prism test, which is this one over 1260, because you'll get less mixes that fall in this area of very bad. So, here our correlation again, a lot better correlation with C1293 compared to C1260 when we are comparing a test method to outdoor exposure blocks. So, I think we kind of know that this test method is better when you're looking at straight aggregate reactivity. However, we do know this is a 1-year test, and no one really wants to wait 1 year also. So that was part 1. Part 2 in these guides is about how to select preventive measures for ASR. And this is C1293 results of one control aggregate with these different SCMs. And what we learned was, or what this test method showed was, everything looks great at 2 years. Again, no one wants to wait 2 years, except this one 30% Class C fly ash, which we kind of knew back then that it would probably not work. But everything else looks great and it should work. And now when you take that same data set and put them into exposure blocks, at 4 years, here's our control. Here is that 30% Class C fly ash, which we saw was not working in the test method, so we're really happy at 4 years. Go to 8 years. Oh, let me go back one slide. And so this is, again, a correlation here on the right, in which we kind of want to be in this area or this area where we get correlation between the test method and the exposure blocks. So if you're down here, if you're below this 0.04, you don't really have cracking in the block. And of course, 0.04% is the expansion limit in this test method. So at 4 years, we're in this happy area where everything looks great. We're getting good correlation between test method and exposure blocks. At 8 years, we started seeing things start to expand, and which then started putting us into this area which we do not want to be in. And then even at 12 years, everything has gone. And we're, wondering what, this is not good. All, these guidance documents and everything have been based on this, this long-term exposure site data, but it took 12 years to see how things have expanded and moved from an area that we wanted to be at 4 years, but then after 12 years, everything has moved into this region which we do not want to be in. And that kind of is how we kind of came into this C1778 and how to improve that guidance document. And that's that data set, but lots of other blocks as well. This is just another one. This is the expansion limit. This is another aggregate out of New Mexico with a whole bunch of different SEMs that showed to be really good in laboratory tests. However, in exposure blocks, after 2,000-3,000 days, they start to fail, which is something we're not expecting. This is another. This is the Sprat aggregate out of Canada. Same thing. Different fly ashes, silica fume, just everything expanded. Another aggregate out of Texas with ternary blends, something we thought would be really good because even the test method showed that it works really good. But it just starts taking off and just not stopping. This is up-to-date data here, and it's just not stopping. And then we'll also look at lithium nitrate. This was a big thing 15 years ago or so to use 100% lithium nitrate, but a lot of these mixes, these are all like 3 different aggregates here, and we thought it would work, but everything does fail out in the field with it. So honestly, actually everything pretty much fails out in these exposure blocks. And is it because our test methods told us to put too little of a prevention level in there to control the reaction? And so this is, again, the correlation between those standardized test methods and exposure blocks. This is an area that we did not want to be in at all, and this is comparing the 14-day test to exposure block data. So, it showed us that we're going to be below 0.1 expansion in our test methods, but everything is failing in the field. And if you look at 1293, it's even worse. 1293 showed us that we're going to be below 0.04% at 2 years, and we are below 0.4. We thought we were going to be good, but if you look at the exposure block expansion, we are in this area which we do not want to be at. So that's kind of the background on why this whole project came about. So what we wanted to do in this NCHRP project between the 3 different universities is to kind of make new exposure blocks, maybe not have that high alkali loadings that we had in those blocks, and also place them in different environmental conditions as well. We put exposure blocks on this project, over 450 blocks, in several different locations across North America. We have 2 sites in Texas, the University of Texas in Austin. We have a site in Port Aransas, Texas, at University of New Brunswick in Fredericton, Canada, and I'll call it their sister site, which is on Tree Island, and then Corvallis, and then Newport, Oregon. Also, we have a site in Lawrence, Massachusetts, and also a site in, of course, Hawaii. So the whole goal of this was to, focus also on lower aggregate reactivity, so more of a R1, R2 aggregates, lower alkali loadings, and be more representative of highway infrastructure mixture designs. And not only that, back then, with a lot of these exposure, or even 1778, all we have in there is just looking at fly ash and slag cement. But we also wanted to start looking at reclaimed fly ash, bottom ash, natural pozzolans, metakaolin, slag cement as well, to put into these 450 exposure blocks that we have placed across the country. These are the different aggregates that we have looked at. Kind of each university had their own regional aggregate, and then we had 4 common aggregates as well, in which aggregate was sent to all 3 different universities for those. And then we also kind of looked at those historical aggregates, which I'll kind of get to at the very end of this presentation. Also, another thing with different compared to some of our older exposure blocks, we do have 1L blocks on this site, and also, again, I kind of mentioned, there's new types of SCMs. There are just pictures of the different sites that we have in the different locations that we have cast on this project. And all that data, we're not going to know what's going on for 10, 15 years from now. So just like we learned so much from the exposure sites that we cast 20 years ago. But so again, they're less severe blocks, new SCMs, again, time. It's going to take time for us this is going to help us improve the guidance or these documents in 15, 20 years from now. So that part of the project, it's, a whole bunch of work, put blocks out there, new SCMs, what we have out there now, and see how we could try to fix our documents in the future. The second part of the project was to, how can we improve and benchmark our current performance and job mixture tests that are kind of being developed now. These are the tests that we all know, the mortar bar test, concrete prism test, and how can we correlate this to these blocks and make things better. So we looked at a couple different test methods. The ASTM T380 miniature concrete prism test. I always like to describe it to being kind of in the middle of 1260 and 1293. Instead of a 1-inch water bar or a 3-inch concrete prism, you have a 2-inch bar. Instead of being at 38 Celsius or 80 Celsius, you're at 60 Celsius. It's kind of in the middle. And another test method is the UNB, so University of New Brunswick concrete prism test. We also sent aggregates off to a federal highway for TFAS testing. And also just looked at different variations of C1293, which is known as kind of a rylum test method, in which you actually wrap the prisms in a cloth that has matched pore solution of the alkalis, just so you try to not get leaching in the test. This is the miniature concrete prism test I kind of just mentioned earlier. It's kind of similar to 1260. You do take concrete again, and you do place it into a high alkaline solution. And again, there's the 2-inch bar, and it's at 60 Celsius, but again, also in the 1 normal ceramic hydroxide. The good part about the test, it's not going to take you 1 year for aggregate reactivity, or it's not going to take you 2 years to look at SCMs for prevention. It is a 56 or an 84-day duration, depending if you're looking at aggregate reactivity or SCMs. The UNB concrete prism test, it's almost kind of similar, in which you have a container here, which is a 6x12 cylinder, but which is also, they made cylinders that were just slightly larger, in which they took a 6x12 cylinder, put it inside this other container, and then filled the outside with a hose solution. And what they try to do, we matched the pore solution, whatever was in the mixture, to be in this outside area of the thing. And also this is at 60 Celsius and at a high temperature of 80 Celsius. So when we look at, for this project, aggregate reactivity, we have the C1260 compared to C1293 here, and this is how they kind of match up. And we do have one aggregate here, which is below that 0.1% expansion in 1260, but does fail in 1293, and we know this aggregate too also fails in blocks as well. So we kind of picked this aggregate here because we know it was a funny one. But we do have good correlation otherwise with the other test methods with all the aggregates. And then this is now looking at T380 and C1293, and we're actually able to get this aggregate here to actually fail in the ASTO T380 test method. So we have good correlation. We look at 1293 and T380. And that is one thing too with 1260. You could get a lot of these aggregates that fall in this region here, but fail in the field, and that's the area that we really stay away from these false negative type of aggregates. So if you could have a test method that could catch that, like T380 can, in a much shorter time period, of 56 days compared to 1 year, I think that's successful. And this is also just looking at all the different aggregates based on how each one of these different test methods or guidance documents says if they're slowly reactive, moderate reactive, highly, or very highly reactive. What we did see was the T-fast, it kind of underpredicted the reactivity more often than the other ones, which I think kind of would make that a little bit less conservative. But overall, I mean, I think they're all are pretty good at, or even, because honestly, someone tells me it's moderate or highly reactive, what does that really mean? It's all based on a whole bunch of data, but I know it's based on expansion values and everything, but overall, the 4 different test methods here did a good job of determining the differences. And when we look at on the project at prevention, again, this kind of goes back to 1778. We know this is our table in C1778, where we kind of go through a whole bunch of tables, and sometimes it can be confusing going through like 7 different tables before getting to this table. And once you finally get to this table in C1778, it tells you your level X, you need 20% FASH, or one of these other different prevention levels. And what we looked at was with these different aggregates on the project, we used the prescriptive approach for highway infrastructure preventions. And what it told us was, for a bridge that has 560 pounds of cement, blah, 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 you're going to be level X or Z, and you need X amount of fly ash. So we used that amount in the mortar bar test, and what it showed was, we want to be pretty much in this region here on this graph here, because that prescriptive table tells us it should work, right? It says 20% FASH, you should work. And what we saw was it only worked for 5 or 6 different mixes. We have lots, and this is looking at 1567 and also T380 results here, but this whole region here, all these mixes should work according to that prescriptive table in C1778, but it does not. Then also for non-prescriptive SCMs, so any of these 5 here, you can't use that. There's no table for it to go there and say use 30% of a blended ash. So you have to use C1567 to first determine how much you need to control it. And that's what we did. We used C1567 with all these different, those 5 different SDMs I just showed. So that's why everything's below 0.1. But when we tested with T380, we kind of in this area of bad. It does not, T380 showed them to not work, whereas 1567 said that they would work. And however, if you actually extend it 1567, so this is 14-day data here, but not really a good correlation between the two test methods. You push out 1567 to 28 days, we did see a better correlation between the two test methods. We are in this area of finding things to fail. We want to be in this area or this area here where the two test methods agree, not in this one and this one. So by pushing it 1260 or 1567 out to 28 days, you get a better correlation. And don't worry about all this data here. I just want to let you know what we did was with all those different aggregates, we looked at C1567, C1293, ASTO T380, the UMB CCT, AR13. So we have all this data now to help benchmark with those 450 exposure blocks that we'll know in the future on how these test methods will correlate to these exposure blocks. So back to this 1778 prescriptive table, which is also in ASTO R80. This is so the whole thing was about how to improve the guidance document in, let's say, C1778. One thing is these levels of SCMs for fly ash and slag cement, we're going to recommend to boost these up about 5% because they are not able to show, in both 1567 or C1293, we are getting things to fail in which they should not. So we're recommending to increase these levels. Adding in natural pozzolans, which is not currently in the table, but only for a lower level of risk, since it's still new. So you could still use them, we're saying, but you have to run a performance test. But at least we're saying minimum 25% replacement if you're in a level W environment. And third thing is some of these high alkali fly ashes, we're saying not permitted. We saw lots of bad behavior with these ashes, and also silica fume. We noticed that we really weren't able to get good consistent types. We looked at several different suppliers, and just to be on the safe side, when you're in a level Y or level Z type of environment, just to be more protective, to not be able to use them as a prescriptive way to mitigate or prevent ASR. Here towards the end here, so what we did also was we have several blocks that we know that failed in the field, have SCMs, and we wanted to look at these different test methods and compare them to exposure blocks that we have out in the field. And what we did was, so we have storage of all these aggregates from 20 years ago, so we're able to, in SCMs as well. So we're able to do these newer test methods as well and go back and see how they correlate to these historical blocks. And these are just, the first column here is 14-day 1260 at 0.1%. There's a 44% correlation between that test method and exposure blocks. 1567, or I'm sorry, if you take it out to 28 days, you have an 81% correlation. Concrete prism test has only had a 28% correlation. So you wait 2 years for the test, but it's really, really bad on the correlation with our outdoor exposure blocks. There's the AR13, which is similar to 1293 with the wrapping, but only had a 13% correlation. ASTO T380 at 63% and UMB CCT at 38%. So we told ourselves, well, what if we then had the exact same test methods and we bring down the expansion limit? So instead of 0.1 for 1567, what if we looked at it at 0.08? And then also if we really brought down the expansion limits. And we had to come up with some idea like what is satisfactory. Of course we're not going to get 100% correlation or anything, but the interesting thing with all this was the 2-year concrete prism test for looking at SCMs really did not provide us any good correlation. This ASTO T380 at 75, or it was 75% correlation at 0.025%. it's not a mortar. It's it's more of a concrete type mix, so it's more realistic, and you don't have to wait 1 or 2 years, right? So it's only a 56 if it's aggregate reactivity, or 84 days with STMs. So it's a lot shorter time period. I think people would actually be a lot happier doing that test compared to a 2-year concrete prism test. So lessons learned since the developments of C1778, the concrete prism test has been reliable. Straight aggregate reactivity, we saw that early on in slides, good correlation between the two, better than 1260 for looking at aggregate reactivity. However, for SCMs, to try to prevent ASR, it was found to underestimate the amount of SCMs, especially when you try to correlate that to the high alkali loading exposure blocks. And some of the key findings is, as I just mentioned, still use 1293. ASTO T380 is recommended to evaluate aggregate activity or preventive measures. ASTM C1777, once properly, benchmarked against T380 or C1293, could be used for SCMs, but we're throwing out this thing about 28 days because we did see that better correlation. But I think we could also maybe go to these guidance documents to try to implement this. Maybe that 28 days is only for severe, like a SC3 or SC4 type of structure, So I think we might have to see if we could put performance or this performance test to see how we could also put them in with risk of a structure. Natural pozzolans, or now, as a prescriptive-based approach. SDM, just as previously recommended, should be increased to better correlate with exposure blocks. Going along. And then, again, all these recommendations may change in the future from that correlations between all these blocks and these test methods. We kind of continue on from that project. We have a new project with ACPTP with airfield pavements, and kind of put that slide there, but I think Jason Eidiger will be kind of talking more about this project here in a couple minutes or about an hour. But any questions? Yes.